tell us, if I find that IA0 is equal to 0, IA1 is equal to some value 2 ampere at an angle of 10 degree or 120 degree, whatever degree, 2 ampere, and if I find that IA2 is equal to 0. So IA0 is equal to 0, IA1 is equal to 2 ampere at 10 degrees, and IA2 is equal to 0. It is telling me that the system is balanced. We'll do this tutorial. IA0, I'm taking just an example, we'll do this tutorial. I have some examples there. IA0 is equal to 0, IA1 I have calculated and found that is 2 ampere at an angle of 10 degree. IA2 I also found it to be 0. It means, it tells me that the system is balanced. The current phasors are balanced and it's having positive sequence because I got IA1 is equal to 2 ampere. Does it make sense?
Yes, sir. Thank you.
Okay, so let's go to the next chapter. This next chapter is a small one and it's called asymmetrical fault analysis. Now we are going to look at asymmetrical fault analysis, the equations, the sequence networks, interconnection of the networks, and then finally determining these values of IA0, IA1, IA2, IB0, IB1, IB2, IC0, IC1, IC2. Remember that we need to know all the three phase currents, IA, IB, IC. To know them, we need to know the respective sequence components. Then we will be able to, so we will have to know all these IA, IB, IC. These are the phase current, actual phase currents. But now the system is unbalanced. IA is not going to be equal to IB or IC. There will be different, and because of that we will have IA1, IA2, IA0, IB1, IB2, IB0, IC1, IC2, IC0. So all those values need to be determined to determine IA, IB, IC. But what we do, we follow that principle. We choose the reference phasor as the phase A, and from there first one is the A phase is determined. When we know the phase A, then we can determine phase B and phase C easily. So let's go to the outline. I will combine the tutorial of that symmetrical components and this asymmetrical fault analysis together. So this is the introduction that we'll go through, and then the procedure for fault analysis, and we'll consider single line to ground fault, double line to ground fault, and of course the three-phase fault that we have already worked in power systems 1. But now this three-phase fault will be considered according to symmetrical component theory, because it's such a good theory. It's applicable to both symmetrical and asymmetrical faults, and then we'll combine the tutorials. So now I am coming to this asymmetrical fault analysis. Asymmetrical faults are happening, or it happens between the phases or between a phase and ground. So if we find that two phases, any two phases, AB, BC or CA, are shorted, that shorting can sometimes be through an impedance, meaning in between phase A and B there is an impedance present, but they are connected. So that will give rise to a condition of asymmetrical fault. Also, we can find asymmetrical fault if any phase ABC is grounded. Also, we can find asymmetrical fault in another form. These two faults that we are talking about here between phase and ground are classified as shunt fault. But if we look at other type of asymmetrical fault, they are called series fault. And those are if a line is broken, a phase is broken, phase A is broken, B and C, they are fine. So it's in the line impedance. And the feature of that type of series faults are such that they come from the unbalance in the line impedances. They can come in a way that does not involve any connection between the lines or phases, meaning we cannot have asymmetrical series fault if A and B phases are connected together. That will give rise to shunt fault. It does not involve any connection between line and ground. If a line is grounded or if a phase is grounded, then it's going to be shunt fault, not a series fault. Series faults come from breaking of a line, change in impedance of the line of one of the phases. It can be possible that all the lines are connected, none of the lines or phases are broken, but the impedance of one line is different as compared to the other two. Then it will give rise to series fault. Also, if we find that a line is broken, other two are fine, it actually changes the impedance of the line, because the line which is broken, its impedance is to be seen as infinity because the line is open. If two lines are broken, two lines impedances are going to be represented as infinity, and they are different from the third one, which is still okay. Is it clear about the differences between shunt fault and series fault for asymmetrical type? So asymmetrical faults are now divided into two categories: shunt fault and series fault. Shunt faults happen between any two phases or any two lines, and it can be in another form if a phase, any of those three phases, is grounded, and those interconnection between the phases or the lines or any phase and ground can be via an impedance, can be directly short circuiting if the impedance value is 0. We call it fault impedance, ZF. It is represented by ZF. ZF is the impedance for fault, and ZF can be 0, meaning a real short circuit. And if ZF is there, meaning some impedance is in between, it's not ideal short circuit, impedance is not equal to 0. So we generalize it using the fault impedance ZF. For asymmetrical series fault, we find that we can generalize it in a sentence: unbalance in the line impedance, and that unbalance can come from real unbalance in terms of impedance. It can come from a broken line, because if the line is broken or the phase is broken, its impedance is going to be infinity. And all other features, it doesn't involve any connection between lines or phases. If there is any connection between any two phases or lines, then it will be shunt fault. It doesn't involve any connection between lines and ground. If that happens, then it's a shunt fault, not a series fault. So in this chapter, we will only deal with shunt faults, not series fault, because series fault itself is much more complicated to deal with. And just to let you know, if we want to learn the series fault analysis, it's another very thick book, about 600-700 pages only on series fault. So that's why I wanted to limit ourselves, because this is only an 8-credit module and we have other sections or chapters to learn. I have limited it to the shunt fault. So the shunt faults, what we are going to consider here: single line to ground fault. Sometimes we write them SLG, or sometimes we write them at LG, line to line fault. So it's L12. Sometimes the other people will say it's face to face fault. It's the same thing. Double line to ground fault. Some people will say face to ground. So LLG, or face to ground, which is also a symmetrical fault. Three phase fault, sometimes we write as LLL, 3 lines. Sometimes we can say face to phases, all 3 phases. They are symmetrical fault, but can also be analyzed using symmetrical component analysis. And also the next one, 3 phase to ground fault. So LLLG, symmetrical fault. So these are the 5 different types of faults. All of them are shunt in nature, are going to be covered in this chapter. Series fault are much more complicated to analyze, and like I mentioned, it's another 500-600-700 page of book. Too much. So we will go to them now. coming to the procedure of fault analysis. So when we want to do the fault analysis for asymmetrical faults, we need to follow the general procedure. First of all, we need to have a circuit diagram. If we don't have a circuit diagram, we cannot go to the next step, which is a boundary condition. So first of all, we have a system diagram. Sometimes we give you question, all text, no diagram is shown. So what the next step will be for us, we have to draw the circuit diagram, understanding the texts from the question paper. When we have the circuit diagram, we go to the boundary conditions. Boundary conditions are what? Boundary conditions are nothing but some equations, voltage and current equations. And those current voltage and current equations, we write them down looking at the circuit diagram and the type of fault, and of course the impedances and other aspects, neutral, if they are present there. So the boundary conditions, meaning the equations for voltages and currents, we write them. When we write them, they will be coming in terms of the actual phase voltages and actual phase currents. So from there we need to do the transformation, meaning we will come to the positive, negative and zero sequence components, meaning positive sequence voltage, negative sequence voltage and zero sequence voltage will be how they are in our equation. Similarly, positive, negative and zero sequence currents will be there in our equations. That's the next step. So we'll now have sequence currents and voltages. So we now have the sequence currents and sequence voltages. We look at them like I was giving the example that IA0 is equal to IB0 is equal to IC0. We may get that IA0 is equal to IA1 is equal to IA2, meaning all the three sequence component currents are equal. So if we look at that equation and apply the simple things that we have learned, the fundamental ones, that if the currents are equal, then it means the circuits from which those three currents are coming are actually connected in series. Similar thing we can mention about the voltage. If we find that three voltages V1, V2, V3, they are same, equal magnitude, meaning these are coming from three different voltage sources, but they are connected in parallel. So that is why they give rise to a condition where all of them are of equal magnitude. If I take another example, if I find that two currents IA plus IB is equal to IA plus IB is equal to I. What does that mean? These are the fundamentals which you know already. IA plus IB is equal to I, which means there are two circuits. One current is coming from one circuit giving us IA, the other circuit is giving us current IB, and these two currents are added to give us I, which means the circuit which is giving current IA and the circuit which is giving current IB are connected in parallel to give us the sum of those two currents as I. Similarly, we can apply that thing V1 plus V2 is equal to V. So if we have the equation V1 plus V2 is equal to V, what we can say about this equation? V1 plus V2 is equal to V. Think about it and you tell me. I gave you three examples already. Out of four, this is the fourth one. V1 plus V2 is equal to V. What do we understand from this? The way I was trying to explain in terms of the connections, series or parallel. V1 plus V2 is V1 plus V2 is equal to V. How can we explain in terms of the connection in series and parallel? Can anyone explain this? Nobody is answering anything. Can you answer? V1 plus V2 is equal to V. What do you understand? How the connection, series, parallel, what is happening?
So it's not in series.
Yes. So one part will be giving us V1. Let's say this V1 is coming from I1 R1. And then V2 is coming similarly from I2 times R2. So now that has to be in series to give us the voltage across the whole thing. for V1 and V2. So we can get the voltage V as the sum of V1 and V2. So they will be in series. So those information now are going to be very useful to do this interconnection of sequence networks. We'll look at the equations of currents, we'll look at the equations of voltage, and then we'll apply that in terms of either going to be series connection or parallel connection of currents or voltages, and we will interconnect the sequence network accordingly. And when we are done with that, then we'll see what information we can gather from the interconnected sequence networks that will help us now to find out IA0, IA1, IA2. When we have IA0, IA1, IA2, we can determine IA. When we have IA0, IA1, IA2, we can determine IB and IC as well. So that's how we will know all the values of the sequence components of currents and all the three-phase currents IA, IB and IC. That is our task in terms of fault analysis in the first place. Is that clear?
Yes, sir.
Okay, thank you very much. So what we do, we draw the circuit diagram like you see here. So in this case, I have shown the fault point on the three-phase system. The phases are labeled ABC, the neutral point is there, which is grounded, corresponding voltages are also shown, and the currents are shown IA, IBC, then they are the phase currents, these are the phase voltages, and fault point is shown with the arrowheads on either side. It means the fault can happen anywhere, we don't know. So all these leveling things have to be done in the circuit diagram. That is our primary task. The secondary task, like I mentioned, the boundary condition. So for any given type of fault, so when we are going to write the boundary conditions, meaning the equations of voltages and currents, then we'll need to consider the type of fault. Is it a single line to ground fault, or is it double line to fault, or is it double line to ground fault, or is it a three-phase fault, or is it a three-phase to ground fault? So we call them boundary equation considering the type of fault happening. Transformation, we do that in the next step like I explained earlier, and we use this equation to get the zero sequence components. We use the actual phase quantities VABC in this case because it's V012. If it was I012, then it will be IABC. A inverse will still be there, and A is the transformation matrix. We can determine the inverse of it using the knowledge from mathematics. And then we look at the sequence components, currents and voltages to the network connection. That's what I was describing. It's written here, so you'll read them later on. And we gather the information, we do the calculation for phase A, and later on we'll do them for phase B and phase C. And when we have voltages and currents, we can calculate the power as well. So let's go to the first example, which is the single line to ground fault. So single line to ground fault, that diagram that I showed there is taken, and here I am showing a single phase is grounded, single line, the line or the phase A is grounded. This is the fault point. The fault point needs to be shown on the circuit diagram. So fault point is F and the current is IA. The impedance, generalized fault impedance is ZF, like I was telling in the beginning, and then the other fault currents will be 0, and the voltages for the three phases are also shown. So IA is the fault current, this is the boundary condition, and IB 0, IC 0. And if we look at the voltage, what is happening here is the phase voltage of A is now going to be dropped in between the fault point and this point on the neutral bus. So it's going to be given as IA times ZF. So that's the boundary condition. Next step is to do the transformation. So the currents are coming in 0, positive and negative sequence form. So IA0, IA1, IA2, A inverse. We put that this is actually A inverse, and the phase currents IA, IB and IC, they are there. We're doing all this manipulation here in steps, and then we finally arrive at this condition. that IA0 is equal to IA1 is equal to IA2 is going to give the value of those three currents as IA over 3. And now looking at this equation, so what do we find? That this positive, negative and zero sequence currents are equal. We go back to what we were just discussing in terms of series parallel connection. So the positive sequence network, negative sequence network and zero sequence networks are supposed to be connected in series. Is that clear now? So we'll draw the three sequence networks and those three sequence networks in their reduced form. Reduced form means, if you remember in power systems 1, we were drawing the reactance diagram and then we had to finally reduce the network to a situation where we will have only one voltage and one impedance. Then we can calculate the current easily. The same thing will happen here. So we'll draw the positive sequence network, we'll draw the negative sequence network and zero sequence network, reduce them to the shortest possible form, and now they are going to be connected in series, because that is what we are getting from the transformation. And once we know IA0, IA1, IA2, we can determine IA. It will be 3 times of IA0 or IA1 or IA2. So this is what we must remember, that when we have a single line to ground fault, all the sequence currents, zero sequence, positive sequence and negative sequence, will be equal. Hence the sequence networks will be connected in series to finally give us the current of phase A. When we have A, we can calculate the phase B and phase C as well. So you will read these equations. I'm just skipping. So what we'll do, these are the networks. So this is the positive sequence network. You don't worry about this line connecting there, that is coming from this equation. So this is the positive sequence network, this is the negative sequence network, this is the zero sequence network, and they are connected in series. So you start with zero sequence, so they connect in series. So this is the interconnection. This line is actually showing the interconnection. You could connect it here as well, not a problem. So you go from here, series, go through, go like that, series and completion, and completion through this fault impedance like this. So as we generalize this analysis using the fault impedance between the fault point F and the neutral, the impedance was ZF, that will be present here as 3 times ZF, that is what is here. And if there is no fault impedance present, meaning it's literally short circuit, ideal short circuit, ZF will be equal to 0, this part will become equal to 0, and this part will be simply short circuited, no impedance present. So we'll get that all the impedances that are coming from these interconnected networks are actually represented by zero sequence impedance, negative sequence impedance and positive sequence impedance. And the currents IA1 from this circuit, we can see, if I consider that IA1 is flowing here and this IA1 is going to flow and it's becoming equal to IA0, they are flowing, then it can becoming equal to IA2 series, becoming equal to IA1. So that's the series circuit. Because of that condition, IA0 is equal to IA1 is equal to IA2. And if the fault impedance ZF is 0, we call it solid fault, bolted. Sometimes they write it like that, bolt, 3-phase short circuit or bolted fault, meaning there is no impedance present. So that's how we do the interconnection, and then we can calculate. So from there we can go to the next type of fault, which is the line to line fault, meaning 2 lines are connected together, A and B in this case. For example, IB and IC are the currents. There will be no current flowing in the phase A because these two are shorted. So we write down the equations for boundary conditions, and we also need to consider the voltage VB minus VC because they are the 2 phases involved, and we also show the fault current. So after doing the manipulation, we will arrive to this 2 equation from this transformation of the phase currents into sequence components of currents. These are the phase currents IA, IB, IC. These are the sequence of components of current that we will get using the phase currents that we wrote in the boundary conditions. So we will now find that Ia0 is equal to 0, whereas then it's not going to be equal to Ia1 or Ia2 like what happened in single line to ground fault. In this case, Ia1 is equal to Ia2, but Ia2 will have a negative sign, or the vice versa. You can say Ia2 is equal to Ia1 but having negative sign, meaning they are actually the same current, same magnitude, but flowing in the opposite direction. If I say Ia1 is equal to Ia2, then what it means, they are flowing in the same direction. But if I say Ia2 is equal to minus Ia1, they are of same magnitude, but they are flowing in opposite direction. They are connected in series, but series opposition because of that negative sign. And the expression is like this: 1/3 of A minus A squared times IB. So that A, we must remember, is that complex number operator 1 at an angle 120 degree. We also need to consider the voltage equation here, VA1 and VA2. So we see that there's a drop because of the fault impedance and the current. So we'll consider that, and finally we'll draw this circuit like this. That's what I was saying, that Ia1 is equal to minus Ia2. So Ia1 is flowing but in opposite direction of Ia2. So that's what, and you can say the same thing like I was mentioning. Ia2 is of same magnitude but is flowing in the opposite direction of Ia1. So that's how Ia1 is equal to minus Ia2. And from the voltage equation, VA1 minus VA2 is equal to this impedance, between the two circuits, and because of the current Ia1. So Ia1 is causing a drop here across the voltage due to the fault ZF, and is causing the difference between the two voltages VA1 and VA2. So that is how they are connected, meaning they are supposed to be connected in parallel. So that's the sequence diagram for the line to line fault. And the most important thing to notice here is that zero sequence network is not shown here. Zero sequence network is not shown, only positive sequence, negative sequence shown here, because if we remember that Ia0 was equal to 0 in the first place, and we got the equation from transformation step, Ia0 is equal to 0, meaning we don't need that circuit because it doesn't have any impact because its value is 0. That's what I was trying to explain the other time when you asked that question, that if we find one of them is 0, it's going to be absent. It's not going to be necessary to be incorporated in the interconnected network. This is the interconnected network, and zero sequence component is not necessarily necessary here, because in zero sequence current is 0, and that zero sequence current is equal to 0. It can come from that star connection, no grounding, delta connection, that kind of situation. Is that clear?
Yes, sir. Yes, sir.
But you will have to go through those equations a little bit at home. So if we consider the double line to ground fault, it's same, two lines B and C are grounded, but it's grounded now. In the previous case it was not grounded, they were just shorted to each other. And again, we generalize, we consider an impedance in between the connecting point of the two lines and the ground, which is shown as ZG, and the sum of the two currents IB and IC will be flowing through that line connecting this point and the ground. So we consider that, and then write down the boundary conditions and everything. So we arrive at this voltage equation. You will go through this, I'm skipping, sorry. So we'll go through this voltage equation and many steps, another voltage equation for VA1 and Ia1, and finally we arrive at the interconnection, we find that IA0 is equal to 0, IA0 plus IA1 plus IA2 is equal to 0. So what does this mean? These three currents coming from zero sequence network, positive sequence network and zero sequence network will be connected to a common point, star point or a neutral point, because these are the three currents coming from the respective sequence networks. So if we go there, this is how it is going to look like. So IA1, Z1, this part is the positive sequence network, this part is the negative sequence network, this part is the zero sequence network, and all of them are being added, IA1 plus IA2 plus IA0 coming common to this common point, whatever name we can give to the common point, or this bus will satisfy this condition. And the other voltage equations are ensuring that they are actually connected in parallel. So if we have a double line to ground fault, we will have to remember that IA will be equal to 0, and sum of these three currents, IA0, IA1 and IA2 will also be equal to 0, giving rise to this interconnected sequence network to be like this. But again, must remember these are reduced forms of sequence network. They will be bigger. Each of them will be bigger or larger as compared to what we see now. They will come from all the generator, transmission line, transformers, motor, loads, everything. Reduce, reduce, reduce. Simplest possible form. Then we bring it here. Same thing we do for negative sequence and positive sequence as well. I want to take a break for you for 5 minutes. Is that okay? It's 1 hour. I think I did not give you a break. So let's take a 5 minutes break, then we'll join, and maybe 10 minutes. Okay, thank you. Hello.
Hello, sir.
Back. Okay, thank you very much. So we can go to the next one, which is I'll come to this slide later on, which is going to be symmetrical fault, three phase. So if it is the three phase fault that we have learned in power systems 1, is showing the circuit diagrams. All the three phases are shorted to ground. We have the voltage equations for the boundary, VA, VB, VC. Simple, we can write down looking at the circuit diagram, IA times ZF, IB times ZF, IC times ZF, and so on. Then we can write down the transformation equation, VA1, we find it like that. We find the VA2 like that, VA0 like that. And again, from the equation, if we simplify them, we find it like that, and then we determine the IA1, VA1, and then we find IA2, VA2, we find IA20, we also find VA0, IA0, we find that IA0 equal to 0. Because it's a three-phase to ground fault, symmetrical fault, so only one component will be present, and this component is the IA1, IA2 and IA0 are absent, which means we don't need to worry about the negative sequence current and zero sequence current for calculation for drawing the sequence networks. So that's why it was just like this: positive sequence voltage, the positive sequence impedance, and the other two are absent, negative and zero sequence. Only the fault impedance ZF is shown here, just for generalization. If it is a solid short circuit, then ZF will become equal to 0. So from this circuit we can now calculate the value of IA1. When we know the IA1, we can calculate the IB1, IC1. They are going to be the same, because there will be no IB2, IB0, no IC2, IC0, because it's a balanced condition now. Although a fault has happened, a symmetrical fault is a fault where the system is still going to be balanced or remain in balanced condition even after occurrence of the fault. But for asymmetrical fault, the system becomes unbalanced due to occurrence of the fault. So for three-phase fault, only one component is going to be present, and that is coming from positive sequence or negative sequence, depending on which sequence we are considering. Normally we consider positive sequence. That's why we saw that only IA1 is present, IA2 and IA0 are going to be equal to 0. But if we considered negative sequence system, then IA2 would be present there, IA1 and IA0 would be equal to 0. Right, so that's the last part, but I need to go back to the slide. In the previous discussion, when I was showing you single line to ground fault, or if line to line ground fault I considered between B and C. Let me go to single line to ground fault. Yeah, I showed it with the example of a fault on phase A or line A. But what would happen? How would the equations change if a fault occurs on either of the other two phases, maybe B or C? It's not necessary that the fault is going to happen or it must happen on phase A. It cannot happen on phase B or phase C and get grounded. It can happen. Any of those three phases can be grounded. So what will happen? How will we write the equations? We can write the same equations, no problem, like IA is equal to fault current, IB is equal to 0, IC is equal to 0, VA is equal to IAZF. We don't need to change anything. Only one thing, if we change, what we'll do, if we say that in an example real life, we find that there is a fault on the line B, not on A. We keep all these equations same, but we will label that B with A. So we'll call it A, this one will become B, and that one will become C. You understand? We don't need to change any of these equations and the following equations. If we have a case where a single line, meaning line B, is faulted to the ground, not A. So what we'll do, we'll change the label of B with A and then follow the sequence. So if it is A, then this one is going to be B, that one is going to be C. And if we find another case, phase C or the line C is grounded, then we'll call that C as A, then this one will be B, this one will be C. And all other equations will remain the same. We don't need to rewrite those equations at all. Is that clear?
Yes.
Okay, the same thing if we go for double line fault or double line to ground fault is the same thing. So double line fault, I showed the example of two phases, B and C are shorted. It does not necessarily need to be like that all the time, B and B. It can be B and C. It can be A and B or A and C as well. So what will happen if we have a case of A and C are shorted? So we label that one as B and then this one will be C. So we change the sequence in such a way the sequence is not changed, meaning positive or negative sequence, like what we did in the previous case. The labelings need to be changed in such a way that the sequence is not changed. So if it is A, B, B, C, C, A, all those three different combinations of double line fault can happen, and we will change the leveling of the phases such that we can still use all these equations retained from the boundary conditions and used in the subsequent stage for the fault current analysis to determine IA0, IA1, IA2, and then the respective phase currents IA, IB, IC. Is that okay?
Yes, sir.
Okay, thank you. I still have that question of harmonics, and I will explain that one maybe in the next class. But let me, the reason is that I wanted to complete this. This is the last slide for this chapter. I wanted to complete this so that we can move to the tutorial side, but I will explain that harmonics question in the next class. Not Wednesday, single class, double lecture one.
No, that's fine. So at the end of the tutorial, you can do that.
Yeah, the time was such that I wasted, or it was wasted 30 minutes for the Teams did not work. So if you have any question, you can ask. You can also email me later on. Okay, thank you very much. Have a wonderful afternoon, and we'll meet again soon.